Hello everyone, I'm Silvia and I'm excited to introduce our paper, EvIL, Evolution Strategies for Generalizable Imitation Learning. This is a new inverse reinforcement learning method for sample-efficient transfer of expert behavior across environments. Throughout our experiments in continuous control tasks, EvIL demonstrates better interaction efficiency, allowing for faster and more effective retraining in both source and unseen target environments compared to prior work. But first, what is inverse reinforcement learning? IRL is an interactive approach to imitation learning. In imitation learning, we usually have one or more example trajectories demonstrating expert behavior, in this case a robotic arm picking up an object, and we want our agent to correctly learn to imitate the demonstrated behavior. The simplest approach to imitation learning is behavioral cloning, where we simply try to predict the expert's action given each observed state. The issue with behavioral cloning is that it suffers from compounding errors. This means as soon as the agent makes one tiny mistake and goes off course, it will find itself in an unobserved part of the state space where its behavior is unpredictable and the chance of more errors increase. An alternative approach, the IRL one, is to take a set of learner trajectories and then try to estimate some kind of distance measure from the set of expert trajectories we have. We then optimize the learner agent via RL to minimize this distance until convergence. This setup is very similar to a GAN, where a discriminator is trying to distinguish the expert trajectories from the one generated by the learner policy, and the learner policy is effectively equivalent to the generator in the GAN setup. The prediction of the discriminators are effectively used as rewards to train the learner policy until convergence, and IRL effectively recovers a reward function that, when optimized, will reproduce the observed optimal behavior. With IRL, not only we don't have the compounding errors issue anymore, but we also obtain a reward that can be easily transferred to other settings. So in the robotic arm case, it might be impossible to transfer a policy from a specific robot to another, but it's a lot easier to transfer a reward function and retrain a new robot on it to be optimal. The goal is the same, picking up the object, but the policy required to do so might be different from one robot to another, as the number of joints or joint ranges might differ. Unfortunately, we find that modern deep IRL methods have two key issues. Number one, we find that while modern IRL methods do a good job at finding a strong policy, they do a really bad job at finding a reward that allows for effective retraining. This is surprisingly true also when retraining under the same dynamics, so in this case the same robot with the same goal. Number two, they recover rewards that are not efficient to optimize and require many interactions with the environment to reach optimality. We start by addressing problem number one. We find that using reward model ensembles, a policy buffer to avoid forgetting previously given out signal, and a few other tricks significantly improves retraining performance, as demonstrated by our ablations. We call this new algorithm IRL++. Now that we have solved our first issue, let's focus on the problem of efficient retraining. Our goal is effectively to increase the area under the curve of our retraining or training function. In other words, to improve the speed and efficiency of training across dynamics given a certain reward function. We start by introducing a technique for speeding up policy optimization, potential-based reward shaping. So here, given a shaping reward phi that assigns values to states, we define a potential-based shaping term f as the difference between phi at the next state s prime and at the current state s. The shape reward r prime is defined as the ground truth reward plus the potential-based shaping term. If we use the optimal value function as our shaping term, we can easily see how our shaped reward turns into the optimal advantage function. The greedy policy with respect to this modified reward is pi star. We only need a planning horizon of 1 to compute this optimal policy. This is why the potential-based reward shaping speeds up RL. It reduces the amount of planning the agent has to perform. It is important to note that shaping does not affect the value of any policy, and therefore it cannot affect the correctness of the overall RL procedure or IRL procedure, but just the speed of convergence. Effectively, our assumption is that the IRL process recovers a badly shaped reward function, and we want to meta-optimize this term to instead obtain an optimal shaping term. But how are we going to do this? Well, evolution strategies. Evolution strategies, algorithms are zeroth order, population-based method and are well suited for meta optimization problems where the objective function is noisy or non-differentiable. So to put it all together, we first use IRL++ to improve the effectiveness and then ES-based shaping to improve efficiency. In particular, we use the ES to evolve potential-based shaping terms, we evaluate their performance and evolve towards the best performing shaping terms according to our fitness function, which again, as a reminder, is the area under the curve of our retraining. It is relevant to note that this method is applicable to both standard RL rewards as well as rewards recovered by our IRL methods. If applied to a tabular setting, we are able to recover the exact optimal value function as the shaping term. Our meta optimization strategy is also successful in Mujoko settings, and we demonstrate EvIL improves speed of training across all tested Mujoko environments. Additionally, we achieve successful transfer to entirely new environments with different dynamics. Specifically, the transfer environments are made up of agents with randomized link lengths and joint ranges, different to the ones in the original environments. This task will clearly require learning completely different policies, a notoriously very challenging task. Thank you for listening, and don't forget to check out our repo where we open source of our code.